Okay, so welcome to Learning Objective 3-4, which is all about conservation of momentum. We're going to be talking about why momentum is conserved for two or more objects that are colliding or exploding. And the explain why is really the focus here. Now, this is going to be a really short video. It's for your reward for sitting through the 17.5-minute long video that you just saw. So let's get into it. Start by remembering that momentum is highlighted in red. And so we're going to consider these two carts right here. So we got two carts with a little spring in the middle. And when that spring is released, the two carts are going to go flying apart. And so they're going to have some velocity out to the sides. We don't know how much that velocity is. We don't know anything about these carts. One might be bigger, one might be smaller. It doesn't matter. So let's ask some questions about this situation. All right, so think about this. As the carts separate, if the red cart's a little bit bigger, you can see that there, and the blue cart's a little bit smaller, which cart is pushing harder? Now, before I answer that question, let's really define what we're talking about. So here we have, in pink, this force, which we're going to label as the applied force from the blue cart onto the red cart. And over on this side, in a little bit darker pink, we have the applied force from the red cart on the blue cart. So I'm asking you, which of those two forces is larger? Now, the evidence that I've given you right here is Newton's third law, and you just watched a video on this. Newton's third law tells you that all forces come in force pairs. And I want you to think about what it says about these forces. Are they force pairs? And what do we know about them? And actually take a second and try to answer this question. Which pushes harder? Yeah, I wasn't kidding. I wanted you to actually think about it. So hopefully you did, because now I'm going to give you the answer. Newton's third law says that every force has a force pair. In this case, the applied force from blue on red is a force pair with the applied force from red on blue. I know that because they're on different objects, in different directions. They're the same type of force. The only difference is that we have blue on red here and red on blue there. Okay, so they are a force pair. And what Newton's third law tells me about force pairs is that they are always equal. And so the answer here is the forces are equal. Okay, next thing. So which experiences the force for the longest time? Okay, now we're going to go use evidence from Newton's third law again, and the evidence is that forces always come in pairs. You can't have a force without the other force. So which happens for the longest time? Is red being pushed longer, or is blue being pushed longer? Think about it. It's a bit of a trick question. Okay, hopefully you thought about it. It's totally a trick question because they happen for the exact same amount of time. Blue pushes on red and red pushes on blue. They have to happen together. And so the times are equal. All right, let's highlight that in orange. Now, if you think back to the Learning Objective 3-3 video, this would allow us to draw some graphs. A graph of the force on the red cart over time and a graph of the force on the blue cart over time. But let's think about what those graphs are going to look like. Well, We just said that Newton's third law tells us that they're going to have the same force. And we also said that Newton's third law tells us that they're going to have that force is going to act for the same amount of time. And so they're the exact same graph. And there's one other thing that we know about this. Sorry, that should have been an orange arrow. There's one other thing we know about this. And that last thing is that if the force and the time are both the same, then the area under the graph, which we would solve for by taking force times time and dividing it in half, because these are triangles, the area of those graphs is also the same. And the area of those graphs is delta P, the impulse, or the change in momentum for those carts. So that means that both carts have the exact same change in momentum. It says it again right here. Both objects gain the same amount of momentum because the area under the force and time graph is the impulse. And that can also be written as the change in momentum. Okay. All right, now, a little bit of a change here. This is how this would actually appear. You would have the same force on R as you have on B. You'd have the same time, but in reality, the peaks would be in opposite directions. And the reason for that is that they have the same impulse in different directions. So this one will have a gain or a loss of momentum, whereas this one will have a gain of momentum. And what's interesting is, since one is gaining momentum and the other is losing it, and those amounts are exactly the same, is that the change, like the total change in momentum for the whole system, like for the universe, is the same. There's actually no change in the system's momentum. One card is gaining, one card is losing, but if you add it up, it's exactly equal. All right, and that brings us to the law of conservation of momentum. This tells us that the total momentum of a system is constant. It never changes. The only way that it changes is if there's some sort of outside force that is acting on the system. Okay? And so when we look at a collision, what's really happening is we have an exchange of momentum between objects. So if you look at this collision, then you can see that this cart has some momentum at the beginning, and we're going to say it has a momentum of 10 kilogram meters per second. And the blue cart is not moving, so it has a momentum of 0 kilogram meters per second. They're going to have a collision, and after the collision, they're both moving. That means that the blue cart now has some momentum, so we'll say it has like 4 kilogram meters per second that were given from the red cart to the blue cart, which means that if the red cart started with 10, it can now only have 6. Because the total momentum has to stay constant according to the law of conservation of momentum. So if you hand over 4 momentums, then you have 4 less. All right. And that is the big law, the most important thing in this unit. So make sure you remember the law of conservation of momentum.